Welcome to a deep dive, one that's going to kind of twist your philosophical mind a bit. I know that you love these big questions, and today we're tackling one that really challenges a pretty fundamental concept in geometry, like the idea of infinity. Can geometry exist without it?
Oh, it's a question that's been around for a long time. Centuries, actually. It's puzzled mathematicians and philosophers for, well, like you said, centuries. And it's led to some, fascinating attempts to build these alternative geometries.
Yeah, we've got a whole stack of sources here from mathematicians and physicists, people who have really grappled with this problem, and I'm super excited to unpack their ideas and see what implications they have, especially for a philosophical mind like yours.
Right, well, let's just start with the elephant in the room, or I guess the infinity in the room in this case. Like, why is infinity even a problem?
Especially for someone with the finitist view.
Exactly. Well, for a finitist, the idea of an actually infinite entity is like inherently problematic. It kind of clashes with a worldview that emphasizes the finite, and the constructible nature of things.
So how does this tension play out in geometry? I mean, we learn Euclidean geometry in school, and it seems to work, right?
Well, it does seem to work on the surface, but underneath, Euclidean geometry rests very heavily on this concept of infinity. Its axioms, definitions, theorems are all full of references to infinite sets, infinite divisibility, and, stuff like that. Think about, like, points on a line,
Yeah.
infinitely many, or lines in a plane, also infinite.
Okay, yeah, I see how that could be conceptually troublesome for a finitist. Like, if our cognitive abilities are finite and the physical world is finite, how can we truly grasp something that's infinite? Like, how can we be sure that it exists?
Exactly, and it brings up, profound questions about the nature of knowledge, the limits of human understanding, even the very structure of reality, like you're saying. So what do we do? How do we build a geometry that aligns with um, a finitist perspective?
Well, our sources explore some pretty fascinating attempts. One early approach involved the concept of finite fields or Galois fields. These are mathematical structures that have a limited number of elements. So instead of an infinite number line, you have a finite set of numbers that you could work with.
Right. Paul Kustanheimo, a Finnish mathematician, he was one of the pioneers in exploring this approach. And he essentially tried to replace the infinite real number field, which underpins traditional geometry, with a finite field.
So it's like swapping out the foundation of the entire system. But if we're limiting the number of elements, wouldn't that drastically restrict what we can do geometrically?
Well, that's the interesting thing. It turns out that not just any finite field will do. Kustanimo found that only fields of a specific size that satisfy certain mathematical conditions could potentially yield a geometry that kind of, resembled the familiar Euclidean one.
So there's this delicate balance between finiteness and preserving the essential features of geometry as we understand it.
Yeah, precisely. And even when you do find these special finite fields, some strange things start to happen. You encounter what Kustanheimo called bad geometric objects.
Bad geometric objects, I have a feeling those might break some rules.
They do. Think about a line in Euclidean geometry. It extends infinitely in both directions, right? But in some of these finite field geometries, lines can loop back on themselves. They can form closed curves. Or you might find that two parallel lines actually intersect at some point.
That would definitely throw a wrench into our, usual geometric intuitions. But for a philosopher, this raises even deeper questions. Like, what does the existence of these bad objects tell us about the relationship between finite and infinite systems? Are they just fundamentally incompatible? Or can finiteness somehow mimic the behavior of infinity under certain conditions?
It's a, deep philosophical puzzle, and it suggests that our intuitive notions of geometry might be more intertwined with the concept of infinity than we realize.
Hmm.
Now, another approach to finite geometry, one that a philosopher might appreciate, focuses on the very act of construction. It's practical, it's tangible.
So instead of starting with abstract axioms and infinite sets, we roll up our sleeves and get hands-on, like the ancient Greeks with their ruler and compass.
Exactly. Patrick Sapes, who is a philosopher and mathematician, pioneered this approach. He argued that we should ground our understanding of geometry in the practice of constructing geometric objects, using a finite set of tools and rules.
Okay. I can see how that inherently limits the system. You start with a finite number of points on your paper, and each construction step adds only a finite number of new elements. So no matter how complex your construction gets, you're never dealing with an infinite number of anything.
Right. And Sapins developed a formal system that captured this idea really beautifully. He defined basic operations like bisecting a line segment or doubling a line segment, all within this finite framework.
Could you give us an example of like how this works in practice?
Absolutely. Remember that parallelogram we discussed? Sapine's system can elegantly describe its construction. You start with 3 points, you bisect one line segment, double another, and boom, you have a parallelogram,
Yep.
all constructed within a finite set of points.
Okay, yeah. I'm starting to see the elegance here. But what about the distance function? Like, how do you measure distances in a system that's built on constructions? We can't just assume an infinite ruler stretching across all of space.
That's where Sapice's approach gets really clever. He doesn't rely on a general distance function that, applies to all points in some abstract space. Instead, he focuses on assigning coordinates to the specific points involved in a given construction.
So distance function isn't some universal concept, but something that's tailored to the specific construction at hand. That's a significant departure from how we usually think about distance.
Yeah.
But what does that mean from a philosophical perspective?
Well, it raises some, fascinating questions about the nature of measurement itself. Is measurement inherently tied to the concept of an infinite continuum? Or can we build meaningful systems of measurement within a finite framework? Sapice's work suggests that the latter might be possible.
Okay, and this focus on construction, this was taken even further by um, John Burke, who developed a system that dispenses with lines altogether.
Yeah, Burke's approach is truly radical. He builds his geometry entirely on points. No lines, just points and the relationships between them.
No lines at all. That's a hard concept to, like, grasp. How can you even have geometry without lines?
It is mind-bending, isn't it? But Burke manages to define a set of elementary constructions and relations that operate solely on points. Think of, things like extending a segment, or like finding the intersection point of two lines represented by pairs of points, or like determining if angles are congruent.
So it's like taking the building blocks of geometry and breaking them down even further, like reducing everything to points and their relationships. But does this system allow for complex constructions?
Surprisingly, yes. What's remarkable is that Burke proved that any construction in his system, no matter how complex, can never grow beyond double the initial finite area that you start with. It's like a finite universe of points with these strict boundaries where geometry unfolds.
Wow, that's an incredible constraint. It really highlights how thinking about finitism can lead to really radical departures from like our usual geometric intuitions.
Absolutely. Now, are you ready to shift gears a little bit and see how a physicist tackled this challenge of finite geometry?
I'm all ears. Bringing in a physicist's perspective always adds another layer of intrigue.
Let's talk about Ludwig Silberstein. He was a physicist who, back in the 1930s, dared to develop a discrete version of special relativity.
A discrete version of special relativity. This sounds incredibly ambitious. Special relativity already involves like these mind-bending concepts like time dilation and length contraction. How do you even begin to like discretize that?
Well, he started with a pretty simple premise. If space and time are fundamentally discrete, then we can label points in space-time using integers instead of real numbers. He introduced this concept of a hodon as the smallest unit of space and a chronon as the smallest unit of time.
Hodon and chronon. I love those terms. They sound so fundamental, like the building blocks of reality itself. So instead of this smooth, continuous space-time, we have these discrete, countable units. But how did Silberstein apply that to the, complexities of special relativity?
He was remarkably straightforward about it, actually. He defined the smallest possible distance as one hodon and the smallest possible time interval as one chronon. From there, he built up discrete analogs for velocity, derivatives, even differential equations. He essentially translated the language of calculus, which is based on continuity, into this finite discrete form.
Wow, that's quite a feat. But I'm guessing it wasn't just a simple matter of like swapping out real numbers for integers. Did he encounter any unexpected challenges?
He did. One of the core principles of special relativity is that the space-time interval between two events is invariant. It doesn't matter how you're moving, you'll always measure the same space-time distance between those events, right? But when Silberstein applied his discrete space-time framework to special relativity, he found that he needed to introduce additional constraints that weren't present in the classical theory to make sure that this invariance held true.
So the discreteness of space-time imposed new limitations on how coordinate transformations could work. Like, what kind of constraints did he have to add?
For example, in his system, to make sure the space-time interval remained invariant, the coefficients in the coordinate transformations had to satisfy a specific mathematical condition, like add BC1. It's a beautiful example of how imposing finiteness can lead to these unexpected and subtle consequences. It suggests that the very logic of a discrete universe might be subtly different from the logic of a continuous one.
It's a fascinating implication.
Yeah.
And it makes me wonder, are these just mathematical curiosities, or could there be, like, real physical consequences of living in a discrete universe?
That's a question that takes us to the heart of the philosophical implications of finite geometry, really. If the universe is fundamentally discrete, does that change how we think about things like causality, free will, even the nature of time itself?
These are big questions, and we'll need to dive a lot deeper into the specific challenges and potential solutions that finite geometry presents to even begin to address them.
It's true. These, early attempts at finite geometry, they were bold, they were innovative, but they also revealed some, I guess you could say, fundamental challenges that any theory of finite geometry has to really grapple with.
So it wasn't just a matter of like swapping out infinity for finiteness. What kind of roadblocks did these pioneers hit?
Well, one of the most persistent and maybe the most intuitive to grasp is the distance function problem.
Right. We touched on this a bit with Sapir's construction-based approach,
hmm
but I'd love to, dig a little deeper into the challenges of defining distance in a finite world. It seems like such a fundamental concept, something we just take for granted.
It is. And Hermann Weyl, a brilliant mathematician, illustrated this problem so beautifully with his famous tile argument.
Okay, the tile argument. I'm visualizing tiles now. Lay it on me.
Imagine, you're tiling a square floor with these like tiny square tiles. Now picture the diagonal of that square. Since you're using square tiles, the diagonal is also going to be made up of a line of tiles, right?
Got it. Yeah, I can see that in my mind's eye.
Here's the catch. If you count the number of tiles along the diagonal, it'll be the same as the number of tiles along one of the sides of the square.
So if we're measuring distance by, like, counting tiles, the diagonal and the side would have the same length. But that doesn't seem right.
Exactly. It directly contradicts the Pythagorean theorem, which tells us that the square of the hypotenuse, which is the diagonal in this case, is equal to the sum of the squares of the other two sides.
Uh-huh. Okay, I see the problem. Our intuitive notion of distance, like based on counting tiles, it clashes with a fundamental theorem of geometry in a discrete space.
Precisely. And this seemingly simple argument has profound implications for any attempt to construct a consistent finite geometry. It raises the question, is our concept of distance inherently tied to continuity? Can we even have a meaningful notion of distance in a world that's made up of, discrete chunks?
So how do we resolve this distance function problem? It sounds like a real impasse.
Well, there have been some ingenious attempts. One approach involves acknowledging that lines in a discrete world, they might need to have a certain width.
Lines with width. That's
Yes.
that's not how we usually picture lines at all.
It is unconventional, but it's a way to try and reconcile this apparent contradiction between, tile counting and the Pythagorean theorem. Jean-Paul van Bendegem, a philosopher, explored this idea. He proposed that lines in a discrete geometry should have a constant width, represented by a large but finite number.
So instead of being infinitely thin, lines have a measurable thickness. I can see how that might change our tile counting approach.
Exactly. This width can be projected onto the axes of your discrete space. So when you measure distance, you're essentially calculating the number of tiles that fit within a rectangle that's formed by the line segment and its width.
So we're not just counting tiles along a line anymore. We're taking into account the area that the line occupies.
Yes, and by doing so, you can actually make the Pythagorean theorem work in a discrete setting.
That's clever.
Yeah.
But are we really escaping Euclidean geometry here? We're still projecting widths onto axes. It seems like we're relying on some underlying Euclidean concepts to make this work.
You've hit a crucial point. It's definitely debatable whether this approach truly transcends Euclidean geometry. Some argue it's more of a patch than a fundamental solution.
So are there any approaches that attempt to define distance in a purely discrete way without any Euclidean baggage?
There are. Peter Forrest, another mathematician, proposed a system where distance is defined solely in terms of adjacency between points.
Adjacency. So 2 points are either next to each other or they're not. It's a very black and white view of distance.
Precisely. He introduces a scale factor that determines when 2 points are considered adjacent. This scale factor, it sets a threshold for how far apart 2 points can be and still be considered neighbors.
So it's like adjusting the resolution of our distance measurement.
Yeah.
Like a small scale factor means a very fine-grained view of distance, while a large one makes things, more coarse.
Exactly. And this approach, like Van Bennegem's, it allows you to recover the Pythagorean theorem. But it also has its critics.
What are the concerns with this approach?
Well, the formula that Forrest uses to define adjacency, it still looks suspiciously Euclidean. It involves squaring the differences in coordinates between 2 points. So again, the debate continues whether this truly breaks free from that Euclidean framework.
Seems like we keep bumping up against the shadow of Euclidean geometry. Are there any distance definitions that completely avoid, relying on those familiar concepts?
There's another intriguing solution, one that kind of blends elements of both Van Benegem and Forrest's approaches. Mathematicians David Krauss and Joseph Skufka proposed a physical interpretation of distance in a discrete spacetime.
A physical interpretation.
Yeah.
I'm curious to hear how they connect distance to something tangible.
Their idea is to think of distance as the distance traveled by a test hodon moving in discrete steps between 2 points.
So instead of calculating distance based on some abstract formula, we're imagining a physical entity actually traversing the space, like hop by hop.
Exactly. And this physical interpretation has some interesting consequences. For one, it naturally addresses the anisotropy problem, which we haven't really talked about yet.
Anisotropy. Okay, I'm intrigued. What's that about?
In many discrete geometries, you encounter this issue of preferred directions. For instance, if you're using a square grid to represent your space, movement along the horizontal or vertical axis might be different from movement along a diagonal.
I see. It's like the space has a built-in bias, like a grain that affects how you can move through it.
Precisely. But with Krauss and Skufka's approach, there are no preferred directions. The test hodon can move in any direction, hop by hop, so the distance function is truly isotropic.
That makes sense. It's a more dynamic way of thinking about distance based on movement rather than a static grid. But does it truly solve the problem of, defining distance in a finite world?
It's definitely a step towards a more physically grounded understanding of distance in a discrete setting, and it highlights this interplay between the mathematical and physical aspects of finite geometry.
This is getting pretty deep, but I'm eager to hear about the other challenges that finite geometry faces. Like, what else do we need to tackle beyond this distance conundrum?
Another significant hurdle is the dimension problem.
Dimension, you mean like the number of dimensions a space has?
Yeah.
But how can that be a problem in a finite world?
Well, think about it. If you have a finite set of points, how do you even assign a dimension to it?
Right. A set of isolated points should have dimension 0. It's like our usual notion of dimension breaks down when we're dealing with discrete entities.
Exactly. So if we want to talk about a two-dimensional plane or a three-dimensional space in finite geometry, we need to rethink what dimension even means in this context.
So are we forced to just abandon the concept of dimension altogether?
Some argue that dimension is inherently tied to continuity and therefore just doesn't make sense in a discrete setting. But that feels like giving up on a fundamental concept that helps us understand the structure of space.
It does. So if we don't want to throw in the towel on dimension, what are the alternatives?
One promising avenue involves using concepts from graph theory.
Graphs, like networks of nodes and edges. I can see how that might be useful for representing discrete structures.
Precisely. Remember those examples of, building geometry on discrete graphs? Well, graph theory offers a way to define dimension that works for these, discrete structures.
How does that work?
Think about a node in a graph. You can talk about its neighborhood, meaning all the nodes that are directly connected to it. Then you can look at the neighborhoods of those nodes and so on. You get these expanding layers around your initial node.
Right. I can picture these concentric layers of connected nodes.
Now, the dimension of the graph, at least locally around that node, can be defined in terms of how quickly these neighborhoods grow as you move outwards. If the number of nodes in each layer increases rapidly, you have a higher dimension. If the growth is slower, you have a lower dimension.
So it's a measure of how interconnected the space is in a particular region. A dense network of connections implies higher dimensionality.
Exactly. And this graph theoretic definition of dimension has some nice features. It can vary from point to point, reflecting the fact that the connectivity of a space might change from region to region. And in cases where the graph is very regular, like a grid, This definition gives you the same dimension as you'd get in Euclidean geometry.
That's reassuring. It's like we're finding a way to bridge the gap between the discrete and the continuous. But we still have that anisotropy problem to contend with, right? Those preferred directions that emerge from a grid-like structure.
We do. But even there, graph theory offers some potential solutions. Remember we talked about introducing randomness into the network to break those biases?
Yes. It was like shaking things up to make the geometry more uniform.
Well, graph theory provides a rigorous way to introduce and analyze this randomness. By using concepts from probability and statistics, we can create graphs that are statistically isotropic, even if they're built from discrete elements.
So it's like we're smoothing out the wrinkles in the fabric of space by introducing enough random variation. Graph theory seems to be a pretty powerful tool for tackling these, fundamental problems in finite geometry.
It is remarkably versatile, but our journey through the challenges of finite geometry isn't over yet. There's one more hurdle we need to confront.
Okay, I'm ready for the next challenge. What else stands in our way?
It's called the identification problem.
The identification problem. I'm not familiar with that one. What's that all about?
This problem arises when we try to connect our, abstract finite geometries to the physical world. Remember how Silberstein defined hodons and chronons as the smallest units of space and time?
Yes. And it seems so natural to try to, link those to the Planck length and Planck time, those fundamental constants from physics.
Exactly. But here's where things get tricky. If we make that identification, and we assume that the maximum speed is 1 hodon per chronon, we run into some strange consequences.
Okay, I'm sensing a but coming. What are the implications of this seemingly straightforward assumption?
Well, the maximum speed would indeed correspond to the speed of light. But what about speeds just below the speed of light? In Silberstein's system, the next possible speed would be 1 hodon per 2 chronons, which is half the speed of light.
I see the issue. We've skipped over a whole range of speeds between half the speed of light and the speed of light itself. It's like our discrete model has created these gaps in the spectrum of possible speeds.
Precisely. And this problem is a general one. It arises whenever we try to map our discrete units onto the continuous quantities that we observe in physics. It raises the question, can a discrete system truly capture the smooth, continuous nature of physical reality?
So how do we bridge that gap between the discrete and the continuous? Is it even possible?
There are a few possibilities. One is to allow for, jerky motion, where an object might move 2 hodons and 2 chronons, then pause for a chronon, and then repeat the pattern.
So it's like a stop-and-go motion at the most fundamental level.
Yeah.
But that feels a bit ad hoc, doesn't it? Like we're forcing the discrete model to fit the continuous world.
It does, and that's why the identification problem remains a major area of research in finite geometry. It highlights the challenges of reconciling the discrete nature of some of our theories with the smooth, continuous reality that we seem to experience.
It's fascinating how something as seemingly abstract as the discreteness of space and time can have such profound implications for our understanding of physics and the nature of reality itself.
It's a testament to the power of these ideas that physicists are taking them seriously and exploring them in, cutting-edge theories.
Speaking of cutting-edge theories, you mentioned earlier that some approaches go beyond just replacing classical geometry with a discrete analog. You talked about things like lattice space-time, non-metrical lattices, and loop quantum gravity. Can you tell me more about how those work?
These approaches are fascinating because they're not just trying to build, discrete versions of existing geometries. They're searching for a deeper structure from which space and time themselves might emerge.
That's a whole other level of mind-bending.
It is, and it's an area of active research, so things are constantly evolving. But let's start with lattice space-time.
Okay, so how does lattice space-time work?
Imagine a regular lattice, kind of like a grid, but extending in 3 spatial dimensions and 1 time dimension. The points on this lattice represent fundamental units of space-time.
So it's like the universe is built on a scaffolding of discrete points.
Exactly. And by introducing a discrete metric, which is a way to measure distances on the lattice, you can start to see how this, discrete structure might give rise to the continuous space-time that we experience at larger scale.
So the smoothness of space-time is just an illusion, a consequence of zooming out far enough from the underlying lattice.
That's the idea. And it's appealing because it offers a way to reconcile the discreteness of quantum mechanics with the continuous space-time of general relativity.
Unifying those two theories is like one of the biggest challenges in physics today.
It is, and lattice spacetime is a contender in that, grand quest. Now, non-metrical lattices take a different approach.
How so?
Instead of relying on a metric to define distances, they focus on causal relationships between points on the lattice.
Causal relationships. You want like which events can influence which other events.
Exactly. The idea is that the fundamental structure of spacetime isn't about distances, but about the network of causal connections between events.
So instead of a grid with like distances marked out, we have this web of interconnected events, each one influencing the others.
That's a great way to put it. The challenge, of course, is to show how a continuous spacetime with the well-defined metric can emerge from this, causal network.
It sounds like an incredibly complex problem.
It is, but there's been some, promising progress. Now, loop quantum gravity takes yet another approach, one that delves even deeper into the quantum realm.
Loop quantum gravity. Okay, I'm ready for another deep dive.
Loop quantum gravity starts with the idea that space itself is quantized, meaning it comes in these discrete chunks.
So instead of space-time being this smooth fabric, it's more like a tapestry woven from tiny threads of space.
A beautiful analogy. And these threads in loop quantum gravity are represented by loops, which are, closed paths in a network.
Loops. So we're back to graphs again.
In a sense, yes. But these loops are more than just like abstract mathematical objects. They carry information about the geometry of space, things like area and volume.
So each loop is like a little quantum of space. And by weaving them together, we create the fabric of space-time.
You're catching on quickly. And one of the exciting things about loop quantum gravity is that it provides a natural way to define dimension in a discrete setting.
We've come full circle, back to the dimension problem. How does loop quantum gravity solve it?
Well, remember how we talked about dimension in terms of the growth of neighborhoods in a graph?
Yes. The faster the neighborhoods grow, the higher the dimension.
Exactly. Well, in loop quantum gravity, you can define dimension in a similar way. But instead of neighborhoods, you look at the number of loops that intersect a particular region of space.
So a region with like lots of intersecting loops would have a higher dimension.
Precisely. And this definition of dimension is not only consistent with finiteness, but it also has like deep connections to the way gravity works in loop quantum gravity.
It's not just a mathematical trick. It's actually tied to the physics of the theory.
Exactly. Loop quantum gravity is a complex theory, but it's a beautiful example of how thinking about discreteness can lead to, profound insights about the nature of space, time, and gravity.
This whole exploration of finite geometry has been incredible. We've seen how challenging this idea of infinity can lead to a completely different perspective on geometry, one that connects to physics, philosophy, and even computer science.
It's a reminder that there's always more to discover, even in areas we think we, understand well.
Okay, before we wrap up, I have to ask about something you mentioned earlier, the combinatorial hierarchy.
Ah, yes, the combinatorial hierarchy. That's one of the more exotic and perhaps more speculative approaches to finitism.
We've gone pretty deep down the rabbit hole already, so why not explore this one too? What's the basic idea behind it?
The combinatorial hierarchy focuses on the physical constants of nature, things like the speed of light, the Planck constant, the masses of elementary particles.
And these are all finite values, right?
They are. The question the combinatorial hierarchy asks is, can we explain the specific values of these constants in terms of, discrete combinatorial principles?
So it's like we're trying to find a numerical code that underlies the universe.
Exactly. And one of the intriguing things about this approach is that it suggests that the universe might be built from a finite number of discrete elements. Perhaps something as fundamental as, like, bits of information.
So it's like the universe is a giant computer simulation.
That's one way to think about it. But the key idea is that the fundamental laws of physics might emerge from the way these discrete elements combine and interact.
So it's not just about space and time being discrete, but about the very fabric of reality being built from discrete building blocks.
Precisely. Now, the combinatorial hierarchy hasn't had as much, success as some of the other approaches we've discussed. It's been difficult to connect these numerical patterns to existing physical theories.
But it's still a fascinating possibility, isn't it? The idea that the universe might be governed by a kind of cosmic code, a finite set of rules that give rise to the complexity we observe.
It's a tantalizing thought, and it brings us back to the question of whether we can empirically test these ideas about finite geometry. Like, could we actually determine if space and time are discrete through experiments?
That's a question that's been on my mind throughout this whole discussion.
Yeah.
It would be incredible if we could somehow, like, see the graininess of reality.
It would be a revolutionary discovery. And some believe it might be possible. The key idea is that if space and time are discrete, there should be like subtle differences between the predictions of classical physics, which assumes continuity,
Wow.
and the predictions of a finite theory.
Feels like looking for those tiny cracks in the smooth facade of classical physics, those places where the discreteness might peek through.
Exactly. One area where those cracks might be visible is in the behavior of dynamical systems.
Dynamical systems. Can you remind me what those are?
Think of a system that evolves over time according to certain rules. It could be a pendulum swinging back and forth, or the weather patterns on Earth, or the orbits of planets.
Okay, got it. So how do these systems connect to the question of discreteness?
In classical physics, we describe these systems using differential equations, which assume that time is continuous. But in a finite world, we'd need to use difference equations, which deal with, discrete time steps.
So it's like comparing a smooth curve representing continuous change to a series of points connected by straight lines representing discrete jumps.
A perfect analogy. And what's fascinating is that even for seemingly simple systems, these two approaches can lead to drastically different predictions.
Really, can you give me an example?
Absolutely. There's a classic example involving a population growth model.
Yeah.
In the continuous version, you get a smooth curve representing the population over time. But in the discrete version, depending on the, specific parameters, you can get chaotic behavior.
Chaotic behavior, meaning like unpredictable fluctuations, even though the underlying rules are deterministic.
Exactly. The population might jump up and down, erratically. This suggests that the discreteness of time can fundamentally alter the long-term behavior of a system.
So if we observe this kind of chaotic behavior in a real-world system, one that should behave smoothly according to classical physics, that could be evidence for discreteness.
It would be a strong indication, but designing an experiment to definitively prove or disprove discreteness it's a monumental challenge. The differences in predictions might be incredibly subtle, and we'd need to rule out all other possible explanations.
It sounds like we're pushing the boundaries of what's experimentally possible.
Yeah.
What a discovery it would be to actually observe the graininess of space-time.
It would be a paradigm shift in our understanding of the universe, and even if we don't find, definitive proof, the search itself can lead to profound insights. It forces us to question our assumptions, to explore new ideas, and to push the limits of human knowledge. It really is. And, it speaks to this kind of deeper philosophical question, too. Like, are we fundamentally limited by our tools of measurement and observation? Could there be aspects of reality that are, so fine-grained that they remain forever beyond our reach?
That's a humbling thought. We think we've come so far in understanding the universe, but maybe there are these like whole realms of reality that are just hidden from our current view.
It is. It's a possibility worth considering.
Yeah.
But even as we're exploring these kind of mind-boggling concepts, it's worth returning to, like, the roots of this discussion. We've talked about the philosophical implications of finite geometry for our understanding of space, time, even reality itself. But how does this connect back to the field of geometry as a mathematical discipline?
Right. That's a good point. We started by questioning the concept of infinity in geometry, but we've kind of strayed pretty far from those foundational concerns.
Yeah, we have. And it's important to remember that finite geometry isn't just this, like, philosophical curiosity. It's a vibrant area of mathematical research with its own set of theorems, proofs, open problems.
So what are some of the key areas of exploration within finite geometry as like a mathematical field?
Well, one area focuses on developing and analyzing different axiomatic systems for finite geometries. Remember how we talked about Euclidean geometry being based on a set of axioms? Well, mathematicians are exploring alternative sets of axioms that hold true in, finite settings.
So it's like rewriting the rule book for geometry from the ground up, but tailoring it to a world without infinity.
Exactly. And these, new axiom systems, they lead to a whole host of interesting and often surprising results. For example, there are finite geometries where these familiar concepts of parallel lines and triangles, they behave in completely unexpected ways.
That sounds like it would, challenge our geometric intuitions to the core.
It definitely does. And it highlights the fact that finite geometry isn't just some limited or simplified version of Euclidean geometry. It's a rich and complex field in its own right with its own unique, beauty and elegance.
I'm starting to appreciate that. So we have the axiomatic approach, but what other areas of research are there in finite geometry?
Another active area is the study of combinatorial structures within finite geometries.
Combinatorial structures, those sound familiar. Didn't we touch upon those when we were discussing the combinatorial hierarchy?
We did, and this branch of finite geometry, it focuses on things like configurations of points and lines, the relationships between different geometric objects, and the enumeration of possible structures.
So it's like taking a finite set of points and lines and exploring all the different ways they can be arranged and connected. Sounds like a playground for pattern lovers.
It is. And it has connections to other areas of mathematics, like graph theory and coding theory.
Yeah, I can see how the discrete nature of finite geometry would lend itself well to those fields. But we focus a lot on the theoretical side of things. Are there any practical applications of finite geometry?
Oh, there are. Finite geometry, it finds applications in cryptography, error correcting codes, experimental design, even computer graphics.
Wow. Those are some diverse applications.
Yeah.
Could you give me an example of how finite geometry is used in one of those fields?
Sure. Let's take error correcting codes. These are essential for ensuring, reliable data transmission and storage in our digital world.
Right. I know those are important for everything from sending messages over the internet to storing data on hard drives.
Exactly. And finite geometry, it provides the mathematical foundation for a lot of very powerful error correcting codes. By representing data as points in a finite geometry, you can design codes that can detect and correct errors that might occur during transmission or storage.
So it's like using the geometry of a finite space to protect information from corruption. That's a really cool application.
It is. And it highlights the fact that finite geometry isn't just an abstract, theoretical pursuit. It has real-world implications that affect our everyday lives.
Wow, this whole deep dive has been such a revelation. We started by questioning infinity in geometry, and we ended up exploring this vast landscape of ideas connecting math, physics, philosophy, even computer science.
It's a testament to the power of curiosity and the interconnectedness of knowledge, really. By challenging our assumptions and exploring, unfamiliar territory, we can often uncover these unexpected insights and connections.
And for our listeners who are ready to delve deeper into the world of finite geometry, we've included a curated list of books, articles, and online resources in the show notes.
Yeah, definitely don't hesitate to explore those resources and continue your own journey of discovery. There's always more to learn, and who knows what other mysteries and wonders await us in the realm of finite geometry.
Until next time, keep questioning, keep exploring, and keep diving deep.